This is chapter 23, Inferences about Means. If you have not printed off the notes and you have access to a printer, you might want to do that so you can have those in front of you and you don't have to then, copy things down. Just as a reminder from chapter 18, if you draw a large enough sample from any population with mean mu and standard deviation sigma, then the distribution of sample means, x bar, will be approximately normal with mean mu and standard deviation sigma over the square root of n. Remember, that was the central limit theorem when we did our penny activity and our population. Think about what the individual pennies looked like. It was skewed to the right. Definitely not a normal population. We calculated a mean and a standard deviation. But then when we looked at taking, say, 5 pennies at a time, or 10 pennies at a time, or 25 pennies at a time, and we looked at the sample means. So, for example, think about the one we did with quarters. Then the distribution of those x bar values looked approximately normal. The mean was the same as the mean for the individual pennies, but the standard deviation we had to adjust because it was sigma over the square root of n. We're going to make use of that central limit theorem in these examples we do for means. So here's our first example. Suppose we have a coffee machine dispenser. It dispenses coffee into paper cups. Maybe you've seen those kind of things at airports and stuff, and they're not as popular now as they used to be. You're supposed to get 10 ounces of coffee in the machine, but the amount varies slightly from cup to cup. Here are the amounts measured in a random sample of 20 cups. The question here is there evidence that the machine is shortchanging the customers? So here's your data. At some point, I'm going to show you the calculator, ways you can use your calculator. So you might want to pause this video and enter the data into your calculator. So for example, the first cup poured out 9.9 ounces of coffee, the next cup 9.7 ounces of coffee, etc. So we want to know if the machine is shortchanging the customers. So first of all, we need to come up with what our null hypothesis is, just like we did for proportions. So our null hypothesis is going to be that the coffee machine is not shortchanging customers, which means that the mean is really 10, because that's what they said it was. It was supposed to fill 10 ounces. Our alternative, if you think about what shortchanging means, shortchanging would mean that the machines were giving less than 10 ounces of coffee, so we are doing a one-sided, left-tailed test. So this would be what we would set up. Now notice how this is different from proportions. We don't have a p here, we have a mu instead because we're talking about means. Other than that, your confidence interval, setting them up, I'm sorry, not confidence interval, but your hypotheses are exactly the same setup as we did for proportions. We do have some conditions. We were given in the problem, I underlined it, random sample, so we were given that it was a random sample, so it's reasonable to assume independence between each cup of coffee. The 20 cups of coffee is definitely less than 10% of all the coffee cups that the machine dispenses. But we also have to check whether or not it's approximately normal. It's important for us when we are using this technique. We need to look at our distribution. We have a very small sample size. It's only 20. Remember that once you're over 40 with our central limit theorem, over 40, we were pretty safe regardless of the shape of our data. But if we have a smaller sample, like 20, we want to make sure that our distribution is approximately normal. So if you take a look here, what I drew was a stem plot. And this stem plot has split stems. On the left side is my stem. This is a good review of what we did earlier in the course. On the left side is my stem. On the right side is my leaf. Now I chose to split it with the stem split it 5 ways. So I would have put a 0 and a 1 leaf on this first spot, a 2 and a 3, 4s and 5s would go here, 6s and 7s, 8s and 9s. So one thing that is important when you split a stem is you do have to have equal amounts of leaves for each stem. So if I had only done 9, like 9.5 represents 9.5, if I had put all the 9s together and all the 10s together, I would have only had 2 really little branches there, and it wouldn't be enough to tell the shape. But you can tell right away when you just draw a very quick stem plot, you can see that this looks approximately normal. It looks like a histogram on its side. So if you're doing it by hand with a small set of data, I recommend a very quick stem plot as a good way to look at your data. Since all the conditions are met, I can say that my distribution of my x-bar values is going to be approximately normal with a mean of mu and a standard deviation of sigma over the square root of n. Remember, because we have a sample size of 20, so don't forget on your standard deviation, we would have to divide by the square root of 20. Now the problem is we don't know mu. Okay, well, not a big deal because we can use x bar instead. But the other problem is we don't know sigma either, so we're going to have to use s sub x. Now I entered the data on my calculator and did one variable stats, and when we did that, you can find out what x bar is and what the standard deviation is. So I will be able to use that information. The problem is because we have these we're using two unknowns, this is going to change our distribution a little bit. And what I want you to do is pause the video, and I want you to read about William Gossett and the t distribution on page 522 in your textbook. If you don't have your textbook with you at home, you can find him on the internet. And I am going to quiz you a little bit about him in our next class, but there's some important information about him and a distribution called the t distribution. And we are going to have to use that t distribution because we don't know the mean and also because we don't know the standard deviation and our sample size is small. Then we're going to have to use the t distribution. So the name of our test, because our conditions are met and because we don't know sigma and we're having to use s sub x, we have to use what's called a one-sample t-test for the mean. So instead of a z-test, we're using a t-test. You have a table. If you look at the yellow papers I gave you, you will see that after the z tables, you actually do have a t distribution table. So our standardized test statistic, remember our formula for this, is the statistic minus the parameter divided by the standard deviation of the statistic. Now this time our test statistic is going to be a t. So that's our test statistic. Our statistic is x bar. Our parameter is going to be mu naught, so it's going to be, in this case, it's going to be 10. And then we take our standard deviation and we divide by the square root of 20. So here's with our numbers plugged in. So we had our x bar value, our mu naught was the 10 ounces of coffee, our s sub x value divided by the square root of 20. So when you work that out, you get negative 3.49. Now this is a t distribution, not a z-score. Somewhat similar, but you'll notice something else I have written here is DF, which stands for degrees of freedom. Now one thing that is true about the t distribution and the t test statistic is the larger your sample gets, the more the t distribution starts to look like the z distribution, the standard normal. So it is important that we mark what degrees of freedom that we have. So ours, to get the degrees of freedom, it's n minus 1. So for our example, n was 20, so our degrees of freedom is 19. And so I'm going to show you now how you find a t distribution, a t statistic of negative 3.49 with 19 degrees of freedom. I'm going to show you how you find out what that means. This is on your yellow paper. Sorry, it's not yellow on here. But if you take a look at your t-chart, and you can find this after the z-tables that you have, and this is also in the back of your textbook or somewhere in your textbook. And on the t distribution, you'll notice in the left column it has degrees of freedom. Well, our degrees of freedom is 19. I have that in red. So here's my degrees of freedom. The values that are in the chart are actually the test statistic values. So this was a t value of 0.688. Well, our t value was, what was that again? Our value was negative 3.49. Now, we'll only give you positive, but that's okay because it's symmetric. So 3.49, we're looking here. Well, it's in between these two values. Here's a t test statistic, and here's another one. Now, if you look up at the top of the column, these tell you the p-values. These are the p-values up here. So it's a little different from the z-table. So what we know is for our test statistic, we know that we get a p-value between 0.0025 and 0.001. And that's enough. Remember a p-value, how do you tell if you're going to reject your null hypothesis or not? We're looking for a p-value that's since we weren't given anything, less than 0.05. Well, these are both definitely very small p-values, so even though we're just saying in between there, that's enough information for us. So what we would go on with saying, the probability that we would get this value, a test statistic that's less than negative 3.49, is between 0.0025 and 0.001. So we could just state that from our paper. And this is how we would interpret it. Since the p-value is so low, we have evidence that the coffee machine is shortchanging customers. We have evidence to reject the null hypotheses, which means, remember, we are accepting the alternative. So that means, if you look back at what we said, the coffee machine is shortchanging customers. So the good news about this is how you interpret a p-value, it's exactly the same as it was for proportions. So that's good news. Here's another example. A company has set a goal of developing a battery that lasts over 5 hours, which is 300 minutes, in continuous use. In a test of 12 of these batteries, the following lifespans in minutes were measured. So we have all these different tests that were done. So the first one, the battery lasted 321 minutes. The next one lasted 295. And the question is there evidence that the company has met its goal? Well, remember, its goal was to last over 300 minutes. Now, remember what you are trying to prove goes in the alternative hypotheses. So I would set my null hypotheses as the mean is 300, which means the mean battery life is 300 minutes. The alternative, that mu is greater than 300, which would be the company has met its goal of mean battery life exceeding 300 minutes. Now, one thing to point out, we never use an X bar. It's always mu for your null and alternative hypotheses. Just like we always use a p and we never use p hat, you always use mu, you never use X bar in your hypotheses. So remember that. My conditions. I'm not told it's random, but I'm going to assume these batteries are representative of the population. And we also know that 12 is less than 10% of all the batteries produced. Now, I didn't specifically say that my batteries were independent of each other. However, these two statements together satisfy the independence clause, that they are independent. So now when we have two means, we're going to have independent groups like we did before. But on this one, we're okay. If you don't mention that the batteries are independent of each other, then that you'd be okay. A lot of times I'll mention that anyway. Remember, we also have to check that it's approximately normal, and so we could look at a graph. What I did, actually, I'd done that here before. Let me show you with my calculator. I had my data in L3. I had put my data for the batteries, and so I set it up to do a histogram. And so if I graph it, here's what I got this time. I'm not sure, this was from a previous time, and I don't know how I set my window, but here is what I got. What we're looking for is approximately normal. We're looking for no skewness, no outliers. So you'll notice that this satisfies that. There's not, it's approximately normal. There's no real apparent skewness, not really any outliers. So we would be okay in that situation. On this one, though, one thing I want to comment, always draw a picture or a sketch. Don't just say it's approximately normal, there's no skewness, no outliers. You must draw a sketch. Even if you do it on your calculator and you just draw a quick sketch, you'll be okay on that, but you have to back it up with a sketch. So make sure that you don't forget that. Because our conditions are met, we can do a one sample t-test for the mean. Now here I have some information just from your calculator. I'll go through the steps as well here so you can see this. Again, I put my data in my, and I have mine in L3. So let me clear out of this. So you're going to go stat, test, and the second one on the list is a t-test. So that's what I'm going to choose, a t-test. Now, I have the data. Now this allows you, if you didn't have the actual data, but you had the stats instead, notice that gives me something different now. I don't even know where it's pulling these out, maybe from the data that I actually have. But you can actually type in the X bar value and the S of X value if that's what you're given instead. But here we actually have the data. So I have the data, and my data is in L3. My mean was mu naught is 300, so you'd label that. You would tell your calculator where where the data was. Frequency you can leave as 1. And then you're going to tell whether it's a two-sided test, which it can be sometimes. In this case, we wanted to know that they exceeded, so greater than 300. And this is just your alternative hypotheses. And then calculate. And when you do that, bingo, there's all your work. So we get our test statistic. We actually also, they don't give me the degrees of freedom, so I would have to know that. N is 20, so my degrees of, N is 12, so the degrees of freedom is 11. It also gives you your x bar value, your s of x value, and this right here where it says p, that's your p value. So we actually get all that information from the calculator, and I have that here printed out for you. So, so here's my test statistic, and I would write that down. So with 11 degrees of freedom, so put a little subscript on it. Here's how I would write out the notation. The probability that I would get a test statistic bigger than that with 11 degrees of freedom is 0.2378. That's my p-value. So think about, what does that mean? Well, that's not enough evidence to reject the null hypotheses. So we would say with such a large p-value, we do not have evidence to reject the claim that the battery life is 300 minutes. Now, I wrote it in terms of the null hypotheses. Notice I didn't say, therefore, there must be, the battery life is 300 minutes. You don't say that. You could also say, we don't have enough evidence to say that the company has met its goal in exceeding 300 minutes. That would be okay to say. But definitely, we have a large p-value, so we don't have enough evidence to reject the null hypothesis. As far as a definition of a p-value, it's the same thing as it was before. If the battery life is really 300 minutes, if the null hypothesis is true, then the probability of getting sample results as extreme or more than ours is 0.2378. Same definition, same way to define a p-value. Last thing I want to talk about, same battery problem, and let's find a 90% confidence interval for the mean lifespan of this type of battery. Good news, conditions have already been met, so we don't have to discuss that again. Your formula, remember, again, this is the wording from the yellow sheet. It's your statistic plus or minus your critical value times the standard deviation of the statistic. So x bar is my statistic, and we already knew that. We already knew s of x. We already know n. What we don't know is how to find t star with 11 degrees of freedom. So let's go to the paper, and you find the degrees of freedom for 11 degrees of freedom. We're doing a 95% confidence interval. So I'm sorry, a 90% confidence interval. So one thing you have to remember is if you're doing a confidence interval, then you've got tails. You've got a tail on each side. Hold on a second. Let me draw a little sketch up here. If you're doing a confidence interval, remember that if it's 90% in the middle, then you've got 0.05 in each tail. And the values you're looking up here is a tail probability, so it only gives you one of the tails. So when you're looking up your test statistic, if it's a 0.9, then you need to look up, for the confidence interval, 90%, you need to look up 0.05. If we had been doing a 95% confidence interval, I'd be looking here because I would split, I'd have 5% left that gets split into two tails, so the tail probability would have been a 0.025. So for mine, it's going to be a 1.796. So I can fill that in here for T star, 11 degrees of freedom, and then you just crunch the numbers and you get your confidence interval. So here's my confidence interval. I am 90% confident that the lifespan of this type of battery lasts between 291.05 minutes and 321.45 minutes. And as far as what does 90% confidence mean, it means in repeated sampling with of 12 trials that I'm going to 90% of the confidence intervals will contain the true mean lifespan of in minutes of the batteries. So again, notice that 300 is captured in this interval, which is why we ended up with a large p-value and we rejected the null hypotheses. So you can kind of see that this works out the same as we did for proportions. So if you do on your calculator, if you do stat, test, and we are looking for a one, let's see, we want not a z interval, we want a t interval. And we have the data in L3, and I want to do a 90% confidence interval, so let's change this and calculate. Okay, so you can see we get our values right here, same thing we came up with when we did it by hand. So you can use your calculator, and hopefully you see the similarities between, good thing my movie's done because it sounds like my laundry's done too. So you can see the similarities between the confidence intervals and significance tests for means and what we did for proportions. So hopefully when we get back to class, we'll be good to go and we can work out some examples.